Yeah, okay, thank you, Ashraf. So yeah, so until now we have seen we have done linear algebra in the last class, हाँ ठीक है. लीनियर अलजेब्रा स्टार्ट हुआ था जहाँ पे एक ये टॉपिक था, लास्ट टॉपिक था वो पॉजिटिव डेफिनेट, व्हाट इज नेगेटिव डेफिनेट मैट्रिक्स, व्हाट इज पॉजिटिव डेफिनेट मैट्रिक्स एंड ऑल. ओके, सो ये टॉपिक्स इंपॉर्टेंट है जब हम बात करेंगे ऑप्टिमाइजेशन की. सो जस्ट यू डोंट हैव टू you don't have to you don't face any problem. Okay, so just for the recall purpose we will first look at what was the optimization problem in this one variable. Yeah, in one variable. Okay, in one variable you have you have one condition known as second derivative test. You have second derivative test. So what was it? It was if you are given any function fx and you have to check if it has local minima or local maxima, then what was the condition? First you have to find the critical points that are you solve this equation first, step 1, and then step 2 you find the critical points. Let's say our critical point is C. Say C is one critical point. Okay, and then you check for f double dash at this value C. Okay, what happened then? If it is negative, then it's a point of maxima, and if it is positive, then it's a point of minima. Okay, so we have seen these things graphically. Yeah. In the last class we have seen how why this thing happens. Yeah, we have seen the why we do this, how this second derivative test works when we were on the topic of differentiation. We have seen what does that it means graphically, why it's negative then it's maxima, and why it's when it is positive then it's minima. Okay, the same criteria will hold for the multivariable calculus also, multivariable optimization problem. Let's say we have let's talk about multivariable. Okay, for multivariable. Okay, so for I will first let's see for two variable case. Like most of the questions come from this only, from two variable. So okay, so you have a in two variable function, a function is given like this. Suppose that a function is given like this, fx y equals to some z. Okay, so see, we have done linear algebra, right? So you can think it as a function from R2 to R. Yeah, or yeah, R2 to R or R cross R to R. Like it is taking two pair of numbers and giving us one variable. Okay, so it can be seen as a linear transformation or something. Okay, okay, so okay, so let's see. So in multivariable case इस टाइप का कोई function given रहता है. Okay, so not going into too much details, I want to tell you something about a thing called gradient. Although it's a part of vector calculus, it's a whole course, but you can like I can tell you something about this. Okay, so just like in the first variable case, we have the first derivatives. Yeah, d by dx. Okay, for the first derivative. Here there is a function with two variables, so we will have two first order derivatives, and we store it in this form. This is inverted triangle, and we store these two here. df, this is partial derivative. I hope you all know what partial derivative is, and we store this as this. Okay, yeah. Okay, so this is called gradient. This is called del or nebula, but yeah, you can call it del or gradient of f. Okay, so you store this. What does it do? Okay, again I'm telling you, I'm not going into too much detail. Just you have to remember one thing. It tells you the direction. It's a vector, right? So the vector always gives a direction. Vectors are always like this, right? So it's a vector. It's pointing somewhere. Now I'm going to tell where it is pointing. So this always tells the direction of the steepest ascent. Yeah. So think it like this. You are suppose that you are on a mountain. So you are on a point on the mountain. So it will tell you the gradient will on your foot. Okay, because fxy equals to z, it will be a 3D mountain or something, 3D curve. Okay, and this clearly this gradient is something of two variables, right? It's a two in it is an R2, right? So it tells you a direction. In what direction it will point out? It will point at the steepest possible direction. Okay, या जहां पे सबसे ज्यादा स्टीपनेस होगी ये वहां पे पॉइंट आउट करेगा. ओके, the opposite of it will be steepest descent. Yeah, so just put negative of the gradient, you will get steeper descent. This is a lot more used in machine learning, like, but it's okay. Okay, so the direction of the steepest ascent you have to remember. This is what the gradient is. So suppose you have a function like this. Suppose you have a some two variable function like x square sine y. So if you do df by, okay, so if you do df by del x, it will be 2x sine y, right? You have to treat other variables as a constant and just derivative with respect to x, then do df by dy. Okay, so it will give you x square cos y. So the gradient will be the gradient vector. It is a vector, right? You always remember that. So the gradient vector will be 2x sine y x square cos. Just remember this thing. This okay. So you can work it out on a 3D Desmos maybe website. Just put this x square sine y there. You will get a mountain shape 3D object, and on that mountain, if it any point on that, and when you see below on your foot the gradient, it will tell you the direction in which the mountain is the steepest, right? So steepest if you are going up. Okay. Okay. And the length of this vector, this gradient, tells you the how steep that ascent or descent is, right? Okay. Okay. So the condition is that, suppose that you are already on the top of a mountain, so there will be no ascent, right? So just like a single variable calculus, just like in a single variable, what will happen at that this point? The slope becomes zero, right? Similarly, here for the two variable case, this gradient will become zero, because there will be no ascent above that, right? You're not going anywhere. Okay. Okay, you just have to remember this. Okay, now I'm going to tell you, suppose that by solving these two, df by put this df dx equals to 0 and this df dy equals to 0, again you will find a two dimension point, and that will be our critical point. You will find critical point like this. Everything is same, the idea is all the same. You find these critical points and just then put them in it, but it will be more it will not a good way to just you can find the critical point, but it will not tell you if it is a local minima or local maximum. So again, just like in the single variable case, here we have a condition, the second derivative condition. Yeah. Okay. Now the idea of positive definite matrix and negative definite matrix will come into the picture. Okay. We will use defined. We will use the definiteness of the matrix. So I remember one day someone asked me what is the criteria for there are how many criteria for finding if a symmetry matrix is a positive definite or negative definite. Yeah. So there was one thing that was Sylvester criteria, if you remember. Okay, that's what I'm going to tell you. Okay, to find if you have like you have done with this, ये हो गया, you found the critical points. Now you have to check that if it is a point of maxima or if it is a point of minimum. So we will make a matrix which is known as Hessian matrix. Okay, it contains second partial derivatives. Okay, so like for the two cross two, or maybe for a two for a fx y for a two variable case, the Hessian matrix H, I can say, will look like you have a second partial derivative of f with respect to x here, then second partial derivative with respect to x, and then with respect to y. Here it will be the same. These both are equal. Okay, it has to be symmetric. I cannot talk about positive definite or semi definedness of a matrix if it is not symmetric. Okay, df by dy square. Okay, yeah. So the second derivative tells you that if this matrix is positive definite, that means one condition was that number one, if all eigenvalues are positive. Okay, that was the first condition. Second condition was that if the first element, okay, let me write this in an easy way. That's a standard way of writing these second derivatives. Many people write it like R, S, S, and T. Okay, okay, so this is R, this is S, this is also, they are equal, it is symmetric anyway, and this is T. Okay, so the first condition is that, second condition for the positive definite, first condition is that if all the eigenvalues are positive, and the second condition is that if this R is positive and the determinant of this 2 cross 2 matrix is positive, what will is determinant? It's RT minus S square. It is positive. Then we will say that it is a positive definite matrix. Okay. So if this happens, if these two conditions satisfy, we say that our point at which this Hessian matrix was calculated, this matrix is calculated on critical points. They are not unknown variables. Okay, they are not unknown. There will be some numbers. We'll check these second derivatives at the critical points. Okay, so when you will do this, if this happened, it is a positive definite matrix, then it is a local minima. That is the point of a local minima. Most of the time we will be using only this condition. Most of the time. Okay? If you remember from the previous class, when we have a positive definite matrix, the quadratic form of it will be a shape of a convex shape. So now from there you can see why it is a local minima. It's a point of local minima. Right? Okay. For the second case, this is negative. You have to check if it is a negative definite or not. For which the first condition is that if all eigenvalues are less than 0, in other words, a concave. And the second condition is that, see carefully, for the negative definite matrix, you always start with a negative sign, that R must be negative, and then RT minus S square should be positive again. So there is a pattern in this: negative, then positive, and if you have more than one variable, or maybe this matrix will grow to 3 cross 3, then the last minor or the third minor of this will have to be negative. So negative, positive. Okay, alternate sign will be there. So then we will say that it is a point of local maxima. Okay. So we will use only these two conditions. And these two conditions are known as Sylvester criteria. We've already discussed this. Okay. So we will use this when we have critical points. After that, only we can use this. Okay. That's right. Okay. So let's see one question. How to use it. Okay, so let's see one question on this. Let me find one question. Okay, see this question. If fxy is equals to x square plus xy plus y square minus x minus 100. So we are given just this, just a two variable equation. It lives in a 3D space. It may look like a mountain or something, and we have to find if there is a minima point or a local maxima point or a local minima point. Okay, so we just have to look at. So see, first condition, first step was that. What was the first step? First step was that you have to find the critical points. So just do df by del x, del f by del x. So the partial derivative of this will be 2x plus y minus 1. Put this equals to 0 and solve. Just make an equation. Yeah. And then do del f by del y. What it will be x. Yeah, x plus 2y. Yeah, equals to 0. Solve it. Maybe you can write it like this: 2x plus y equals to 1, and then multiply it by 2 and then subtract it from the second equation. It will be 4x plus 2y equals to 2, and then x plus 2y equals to 0. So these two will be cancelled out. Minus minus minus. This will be 3x equals to 2. So x will be 2 by 3. Yeah. Just put them in the equation and you will get y equals to minus 1 by 3. In many situations, it is not as easy as it is looking right now. In many situations, you may get x to be 2 by 3 or 0. Yeah, there can be two roots. ठीक है. So उस केस में क्या है कि हर टाइप का कॉम्बिनेशन लेना होगा. We'll do these types of questions later, but I'm just telling you for now. Okay, just don't ignore these small steps. Okay, so x or y. So we have a critical point. It is 2 comma 3 and minus 1 by 3. So this is our critical point. Now we have to find r. What was r? It was the del 2 by del x square at this point, 2 by 3 minus. Okay, we are sure that at this point, at this 2 comma 3 and minus 1 comma 3, 2 by 3 and minus 1 by 3, you will surely have the gradient 0. That means either we are at the local minima or either we are on the local maxima. Okay, now I'm looking at is this local minimum, local maxima with our conditions above. So what will be the second derivative of the first the equation? Yeah, it will be 2 only. It will be 2 only. So no point of putting these values. Okay, similarly, S was del x del y or del y del x. It will be always same. You don't have to worry about that. So del f by del y will be 1, or del y del x will be 1. Yeah, it's fine. Yeah, is it fine? Then t, again, if there is some values, you have to put these critical points on that. Okay, I don't have any value. It's a constant, so I'm just writing as it is. Now check rt minus s square. It will be 4 minus 1, that is 3, that is positive, and r is 2, that is also positive. that indicates that it is a point of local minima, right? It's a positive definite matrix. So for a positive definite matrix, it's a point of minimum. Which point? This point. This 2 by 3 and minus 1 by 3. Now, okay, this is how you do. Now, in many situations, in economics or mathematics or physics, anyway, there is not direct optimization problems. Yeah, there are always some constraints on which we have to check our uh, optimality of the curves. Okay, so now I'm going to talk about constrained optimization. So how does it look like? Okay, how does it look like? So suppose that fxy is given like this. Okay, and it is, we have to maximize it with some constraint x square plus y square equals to 1. Okay, suppose we have to do this. So you can look it like this. Suppose that we have this is 3D plane, and this is representing a circle. Okay, this is representing a circle. Yeah, I'm telling you what is the problem we have. So this is some circle on this. This, it is flat on the surface, right? And then we have a curve. I don't know how it will look, but maybe we can look it like this. It's a 3D mountain we have, and नीचे एक curve है. Okay, so for a 3 cross 3 matrix, what is the criteria? You have to check for 3 minors. Maybe you can check for eigenvalues. If all the eigenvalues are negative, it's a negative definite matrix. And if you have to go from the minor perspective, then you have to check for the first minor should be negative, then positive, and then negative. It will be the alternate sign. If it is not following any pattern, if it is negative negative, then it is indefinite. We cannot say anything, or maybe semi negative. Is it okay? Yeah. See, so this is our problem. ठीक है, अभी यहाँ पे क्या है कि हम ये क्या करेगा, इस माउंटेन को ऊपर से बाउंड करेगा. It will bound our mountain from here. It is looking so easy. Maybe it is not it will be a simple slope, simple mountain, and you can clearly see that, oh, okay, this is the point of maxima. Or it may be look like the mountain can be look like some this shape maybe, and there is then this will be the level curve. I've told you about the level curve also. So is the problem clear? कहाँ problem है हमें? So there will be so many level curves. If you know what level curve is, so if you have some mountain, then like condition, and then at you fixed one some height. Okay, you fix some height, this type. So this is the level curve or contour of this curve, a particular contour. Okay. Okay. So just take a bird eye view from here. Uh, yeah. Just try to look things from here. You will see that this curve will look like this. This is our the set or the constraint in which we have to maximize these values, and the contours for this case will look like this. Okay. So there will be many uh, contour lines on this. Like suppose that one contour is here and one contour line is here. So when you look from the above, you will see this. Okay. Now what going to tell you that I'm trying to tell you is what I'm going to tell you is that just focus on these points, some special points, which are just touching the constraint equation and the special lines which are just touching this. Okay. Okay. I know that the local minima or maxima will always be on these points only, on these points only. I don't have to look outside this, because that's the meaning of our constraint. We have to just be on this line, x square plus y square equals to 1. So due to our constraint, all the minima or maxima are these points also, these 4 points only we have to look. Is it okay? Now just try to focus on one of this touching point, where it is touching. Just uh, yeah. So we're just touching this. Okay, so we have as a constant and a contour line like this. I'm just focusing about on this. This is our constraint line, suppose, and okay, and this is our function which we have to maximize. Then at this point we have to check if it is a point of maximum or minimum or not. Okay. So why contour are important? So see, when you are on a contour, when you are on a mountain, and then the contour means the you are not going above or down. You are not going up or down. You are just on a. Okay, let me draw one more time. Just you have some mountain like this, and there is some curve like this. Okay, so this is called a contour curve. Suppose that there can be many contour curves. See, when you are on this, suppose that you are on this point and you are just circling about on this, you're not going up or down. So what will be the steepest point here? Where should you go? So the steepest point will be the perpendicular point. Yeah. So the gradient will be perpendicular to these both. Okay. That means that for the both the curves, the gradient will be perpendicular. Okay. So suppose for this red contour line, the gradient is this. The length of the gradient may change, right? So gradient will be this, and for the blue line, for the blue the constraint equation, we have a gradient like this. So the length can be different. This is the main idea. Okay. So the length of the vector can be different, but they both are perpendicular. Or I can say that they both are proportional to each other. Both the gradients are proportional. Okay. So the gradient of this, our constraint, suppose that gxy is equals to some is equals to our gradient of the contour or the gradient of our equation, and with some proportionality constant in between. Generally we denote it like with lambda, and this lambda is also known as Lagrange multiplier. Yeah. Now this is hard to tell you why malab, this vector, how this vector is representing only the steepest point without studying vector calculus. But I hope you got the idea. See, we just have to do one thing. We have two equations. Okay, one is the constraint and one is our the function which we have to maximize. We just look at the gradient of these two. The gradient of both the gradients should be proportional to each other, and the proportionality constant we have is Lagrange multi. It's called as Lagrange multiplier. Okay. With the help of this, we can solve. We have here for a two variable case. We have del g by del x, then del g by del y equals to lambda times del f by del x, del f by del y, and solve it. You have to find x and y. Okay, but the problem is that there is only two equations and there are three variables. One is lambda. So the third, you will get these two equations. Yes, you will get dg del g by del x, maybe minus lambda times del f by del x equals to 0. Okay. First, second, del g by del x minus lambda times del f by del y equals to 0. And the third equation will be our constraint only, whatever the constraint is. The third will be our constraint only. Okay. Okay. So with this method is known as Lagrange multiplier method to find the maxima or minima of any point, any 2 points. Okay. So let's start with one question on this. Suppose that okay, see this question. Okay. Where it is, yeah. Okay. So this is our question. This is the uh, we have to minimize this subject to this constraint. This constraint can be written like this also. You don't have to worry about this equality sign, inequality sign. You can just take it from here. Okay. So remember what was the first equation? It was del g minus lambda times the condition. Okay. Okay. So you can write it. Just take one. Let us denote L to a whole function with the lambda multiplier. So just take 2xy minus lambda times our constant 9x square plus 4y square. You can take minus 36 on this side and write it here, or you can leave it. You can just leave it, or maybe do it again later. But it's okay to write it also. It doesn't matter. Okay, so this is our L. So first thing you have to do is just find dl by del x. Okay. When you do this, you will get 2y minus 18 lambda x. Rest of them will be 0. Then find del y. The partial derivative of with respect to y. Okay. You will get 2x minus 8 lambda y. And the third equation you will get, see, you can directly write it our third equation was this only, but you can find it from here also. How? Just derivate with respect to del lambda. No need to do it this actually. It's okay. So with respect to lambda, there will be minus time 9x square plus 4y square minus 36 equals to 0, or it is nothing but minus 9x square plus 4y square equals to 36. So you have three equations, 1, 2, 3. Okay, this is not equation. Okay, now this is equation. So you have three equations, 1, 2, and 3. Just we have to find three variables, x, y, and lambda. Okay. Okay. So let's do it. From the first equation, we have 2x minus 18 lambda y lambda 2y minus 18 lambda x equals to 0. That will give y equals to 9 lambda x. Okay. From the second equation, we have 2x minus 8 lambda y equals to 0. That will give x equals to 4 lambda y. Okay. Okay. And now we have now we can put these two into the third and then solve it. So from the third equation, we have 9x square plus 4y equals to 36. Or you can just replace y here. Yeah, see, it will be easy. So x will be equals to 9 lambda 4 lambda 4 lambda y की जगह पे 9 lambda x. So x will be equals to 436 lambda square x. So this will be x minus 36 lambda x equals to 0. And then x equals to 1 minus 36 lambda square equals to 0. Okay, now either x can be 0 or 1 minus 36 lambda square can be 0. But if it is 0, then we find that lambda equals plus minus 1 by 6. The solving, you will get this. Okay. Now x cannot be 0. Because if x is 0, then if this happens, then fxy will be what? 2xy. So at 0, it will become 0. But that of course it is not it will not be the point of minima, because in our condition 9x square plus 4y equals to 36, and like it is allowing the other quadrants of also, that implies that it is allowing for values of negative values of x and y. That means it can go to go below that. So just we will work with this only. Okay. So now similarly we have y equals to 9 lambda x. That implies that y square will be 81 lambda square x. But that means it would be 81 by 36 is putting lambda x square. Okay. Squaring both sides. I got this. Now this will also implies that 36y square, yeah, equals to, or you can solve it, yeah, it will go from 9 by 4x square. So you'll get 4y square equals to 9x square. Put in 3. Put in equation 3. What was equation 3? 9x square plus 4y equals to 4y square equals to 36. Okay, and you will get 9x square plus 9x square equals to 36. That will give x square equals to 4. Yeah, so x will be plus minus root. That would mean that 4y square equals to 9x square, 18, and you will get y equals to 18 by 4. Y square equals to 18 by 4, and that will give y equals to this 9 by 2, or 4.5. So you will get plus minus 4.5. Okay, under root plus minus 4.5. Now you have both the points. You have x equals to plus minus root 2 and y equals to, and you have function okay. So again we have to find the minima. So if we take both the signs to be positive of the same sign, then it will not give minima. Yeah, if they are both positive, then it will be a positive number. But we have clearly we can find a negative value clearly by taking opposite signs. Okay, and due to symmetry, we don't have to check for all the cases. Just take any number to be positive. Just take this minus root 2 and this 4.5. You cannot take both positive and both negative. If you take both negative, it will again be a positive number. It will not give the minimum value. So fxy will be 2 times minus 2 into 4.5. That's minus 9, and that's 6. Okay. So this is all about the Lagrange multiplier method. See one thing. In theory, I told you that I have taken the constraint this side and the number this side, but that does not matter. If you are familiar with if you are clear with the idea, it does not matter. Of course, because what is this lambda? Lambda is just some constant. I don't know what constant it will be. But I can take lambda this side, it will be 1 by lambda. And then again denote it as lambda or some delta, anything. It will not matter. But in many books, standard books, they have taken like this. The problem this side and then lambda times the constraint. This is the standard way you find in any other YouTube guy will tell you, or in the classrooms also. This is how it is follows. But the subtle idea was that only that they both the gradient will be proportional to each other, and proportionality constant can be in any either side. It will not matter. Yeah. Okay. So this is how Lagrange method works. you find Lagrange you use Lagrange multiplier method by putting just starting from this, then finding partial derivative, and then doing finding the critical points, and you just plug and check. Nothing. Okay. Let me give you a hint for the second problem, which is again for the on the Lagrange method. See this problem may look big, but not a big deal. Okay. So again, start with L. Taking L, defining L. L will be our main problem. That is 100 minus this thing, and then minus lambda or plus lambda. It does not matter. Okay. What is our constraint? Ex plus y. It will go this side. Now they are clearly saying that you have to check in the first quadrant only. Okay. Start. First we have to find the partial derivatives. So it will be e to the power minus x minus lambda ex. Just check. Okay, let me also check. Yeah. This x will not be there. It would be 1. Okay. First equation. The second equation will be with respect to y. It will give you minus y minus lambda. Okay. From this, you can have e to the power minus x equals to lambda e. Or from here, you will get e to the power minus y equals to lambda. So what will be e to the power minus x by e to the power minus y? It will be lambda e by lambda. That would be e only. Okay. The third constraint, the third, again you can do del L by del lambda and then do, or you can just clearly write the constraint. The constraint is ex plus y equals to e to the power e divided by e minus 1. Okay. So these two equations we have. See, from the first equation I can write it like this also. E to the power minus x equals to e into e to the power minus y. That will clearly give me e to the power 1 minus y. And now I can compare the powers. It will give minus x equals to 1 minus y. Or I have okay, so I have x equals to y minus 1. Okay. So from the putting this x value in the in this, we get e y minus 1 equals to e to the power e minus 1. Just try to find y from here. It will be ey minus e equals to e minus 1. Ey equals to e divided by e minus 1 plus e. Solve it. E minus 1 e plus e square minus e divided by e minus 1. So, okay. Yeah, so ey is this. Is everything all right? Was there y also? Yeah, there was y also here. Plus y equals to this. Okay, so there is one y here also. Okay, so take y common, get 1 plus e or e minus 1, e plus 1. So y will be e plus 1 into e minus 1. That will be e square minus 1. Okay, now our x was y minus 1. So replacing that would give e square minus e square plus 1 divided by e square minus 1. So it will be 1 divided by e square minus 1. So the critical points are, so our critical values are 1 divided by e square minus 1 and y is e square divided by e square minus 1. Okay. Okay. So the optimal solution is achieved. We have some only one critical point. Nothing to check here. You like they are saying that it is a point of optimal point. Okay. We don't have any option for other values like x equals to 0 or some combination. We have some only one point. It have to be maximum only. So these points are our x star and y star only. Okay. No need to check other points. Just clearly see. So now what they are asking? They're asking for what is the value of y star divided by x star. So just give them. It will be e square divided by e square minus 1 and 1 divided by e square minus 1. These two will get cancelled. Under root e square, that is an e only, and that's 2.7. So that's our final answer. Okay. So that's how you do questions on Lagrange multiplier. Just practice more and more questions on this. It's easy. Easy topic. You're already familiar with differentiation and all, and you should not skip it, or you should not leave it in the exam hall. Okay. Okay, so these are the problem for constraint, one constraint only. Now, there are situations where there is not only one constraint, there are more than one constraints. Hmm? So, suppose, for example, a problem with fxy is our function, and there are more than one constraint. Like suppose that one constraint is g1 xy, some less than some c1, or then g2 xy less than equals to some c2. So in these types of problems, we use LPP, linear programming. So okay, so let's start with one problem directly. Hmm? Let's put one problem here. It's a very easy topic. You just have to make a diagram. Okay, see this problem. There are three constraints here. Okay, just this is a I think 2022 IT Madras jam problem. So I have these equations of these constraints with me. First one is 5x plus 4y is less than 20. Remember, you always have to draw a diagram. You just have to draw lines and then check for optimality. Okay. So for the first problem, the first thing you do is that replace this inequality with equality. Then find the points of x or y where they are intersecting. Put x equals to 0. If you put x equals to 0, the y will be 5. And when you put y equals to 0, x will be 4. The second equation is 3x plus 5y equals to 15. It is actually less than equals to 15, but I'm telling you again that you have to just look for equalities. Okay, let me write it. Put x equals to 0, you will get 3, and when you put y equals to 0, you will get 5. And the third constraint, it is 2x plus y less than equals to 4. So 2x plus y equals to 4. Make a box. Find the intersection points. When x equals to 0, y will be 4, and when y equals to 0, x will be 2. Okay. Now we will draw the line. Let's see. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, see the first line? We have the 4, comma 0 and 0, comma 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. The last constraint is telling us we have to just stay in the first quadrant only. So the first line will be from 5 to 4. This is our first line. The second line is 5 comma 0 to 0 comma 3. 5 comma 0 to 0 comma 3. So this is our second line. The third line is 0 comma 4 and 2 comma 0, 2 comma 0 and 0 comma 4. So the third line is this. Okay, now the conditions with equality are telling us that the first is telling us to look for the reason which is less than 20. Huh? This black line. So under 20 means if you put 0 comma 0 here, if you put 0 and 0 here, you will get 0 and 0 is less than 20. That means that the reason for the first line is contains the origin. Okay, so the first line is taking these points. This is the first, this is pushing here, this reason is pushing towards the origin. Similarly, the second reason is also pushing towards the origin, it is also less. Similarly, the third reason is also pushing the reason to the origin side. Okay, yeah, so you have to take the common reason. So this is the common reason. It is also known as feasible reason. Feasibility means here we will check the optimality. We don't have to go beyond that. So there is one special point here, this point. It is the intersection of red line and the blue line. So just write the red equation, 3x plus 5y equals to 15. And the blue equation, that is 2x plus y equals to 4. We have to find this common intersection point. So you can just multiply it by 5. You will get 10x plus 5y equals to 20, and then above one is 5y equals to 15, and then subtract both. You will get x equals to 5 by 7. And then when you solve for y, you will get y equals to okay, just put in this and solve. Two comma 5 by 7 plus y equals to 4. Then y equals to 4 minus 10 by 7. 28 minus 10, 18 by 7. So y is 18 by 7. Okay. So this point is 5 by 7 comma 18 by 7. All the boundary points you have to check. This point is 0 comma 3, and this point is 2 comma 0. Now we have 3 points, 2 comma 0, 0 comma 3, and 5 by 7, comma 18 by 7. And we have the main thing, in economics terms, you say it like a cost function, something, now. So z equals to 2x plus 3y, or profit function we have to maximize. So 2x plus 3y. Put these all and check where it is happening to be the maximum. So this is 2 into 2, that is 4. This is 3 into 3, that is 9. Okay, for this case, it will be 10 by 7 plus, 54 by 7. So this will be 64 by 7, and it will be 9.14 something. So clearly this is giving the maximum. Okay. So, and the maximum value is 64 by 7. So I think they were asking for the maximum value, the optimal value. Yeah, so 64 by 7. So this is the correct. This is how you do LPP problems. Just try to find the feasible reason by making diagrams, and then you do. Okay. So just take one problem as a homework. Yeah, take this problem. Try solving this problem, and comment the answer if you have done that. It's a similar problem, nothing, no big deal. And after that, we will see what will happen if we have three variables. Okay, two topics are left only for three variables case, and what is the dual of the problem. Okay, so we'll do that in the next class. Start solving this. If you have any doubt, you can ask me in a group or something. Okay. Okay, so we'll meet in the next class.